In this video we're going to talk about the atomic theory and then some of the laws that led to the development of the atomic theory. So whenever I talk about atomic theory, I like to mention Antoine Lavoisier. He was a very important scientist working in the second half of the 1700s. He's often called the father of modern chemistry, and that's because he was one of the figures that brought about what has come to be called the chemical revolution. He and others working with him disproved the phlogiston theory. This was sort of the proto-chemistry theory that existed before modern chemistry. This was the idea that when things burned, they released something called phlogiston, and all matter was made up of this phlogiston, which was sort of fire, and there were a couple kinds of earths and air and water, and sort of we recognize that as being, nothing like the modern chemical theory. Some of his work, and what's most relevant to what we're talking about with atomic theory, is he is credited with being the first person to explicitly state the law of conservation of mass, and we'll talk about that more on the next slide. He was the first person to propose the modern definition of an element, and the textbook that he published in 1789 was very influential for the next 100 years. Now, unfortunately for Antoine Lavoisier and for science, being a scientist didn't really pay as a job back in those days, and so his full-time job was that of a tax collector. And you can probably guess from his name, he was from France, and if you know much about European history, the French Revolution was going on in the 1790s, and tax collectors didn't fare very well. So, unfortunately, he was beheaded in the terror following the French Revolution. Even though there's no evidence that he was corrupt, he and a lot of his contemporary tax collectors were unfortunately executed. Now, I think I talked about the law of conservation of mass in the videos from last chapter, but just to recap, the law of conservation of mass says that during a chemical change, matter, or mass, is neither created nor destroyed. And what this means to a chemist, and the way that Lavoisier studied it, is he would enclose reagents in a bell jar, and then he would allow them to undergo whatever type of chemical reaction they underwent. Very often that was a combustion type reaction where he was heating them. But because they were contained in a bell jar, none of the material was allowed to escape. And what he would do is he would very carefully measure the mass of the reagents. In one of his most famous experiments, he was looking at the decomposition of what we now know as mercuric oxide. And then, because nothing was allowed to escape, he would then very carefully measure all the masses of the products. And what he found in this specific reaction, and in all the other reactions he studied, is that the masses of his product materials were always equal to the masses of the reagent materials. So when he collected the products of that reaction, the liquid mercury and the oxygen gas, the sum of those masses always added up to the initial mass. And so just doing this once would sort of be an observation, but when you do it over and over again for this reaction, and over again for lots of different reactions, eventually that's collected into a law if your results are consistent. In this case, we got the law of conservation of mass. Two other important laws that were developed around the same time as the law of conservation of mass are the law of definite proportions and the law of multiple proportions. In the law of definite proportions, what it said was that all samples of a pure compound contain the same elements in the same proportion by mass. They didn't know why. This was just an observation. And the same thing with the law of conservation of mass. There's no attempt to explain why mass is conserved. It was just observed that in all chemical reactions, mass was always conserved. The law of multiple proportions is a little bit more involved. What this was saying is that when any two elements react to form more than one compound, a fixed mass of one element will react with the mass of the other element in a ratio of small whole numbers. And so, sort of what they found is, 1 gram of copper would react with 0.558 grams of chlorine, or 1 gram of copper would react with 1.116 grams of chlorine, right? And they noticed that the ratio of the masses of chlorine that the copper would react with was 2 to 1. And they always saw this. They always got whole numbers when they compared, how much chlorine copper could react with, or how much, magnesium oxygen could react with. They always got whole number ratios. They wouldn't see fractions when they did this. And so laws are just sort of collections of observations. There's no attempt to explain why. If you remember from things we talked about last time, our big explanations are theories. And so the theory that explains the law of conservation of mass, the law of definite proportions, the law of multiple proportions, several other laws that were developed around the same time, is the atomic theory of matter. And so there were several parts to it. And if you remember, when we talked about laws and theories, laws are often more simple statements and theories are often a lot more involved, as would be expected, because laws are just telling us what happens, whereas theories are explanations. And so we would probably expect that in order to state a theory requires a little bit more work. And so it depends on which textbook you look into or what source you go to, but the atomic theory is often broken down into 5 postulates. And so the first is that matter is composed of exceedingly small particles called atoms. And an atom is the smallest unit of an element that can participate in a chemical change. Now, in Dalton's time, they thought the elements were indestructible. It was not possible to get any smaller than an atom. Of course, we had to revise the theory, right? We still use the atomic theory of matter today, of course, but we had to revise it from Dalton's theory as more experiments and more evidence became available. And so now we know that atoms are made up of smaller subatomic particles, but an atom is still thought of as the smallest unit of an element that can participate in a chemical change. And so if we have a sample of an element, it only consists of one type of atom. And that has an atomic number that is characteristic of that element. And it's the same for all atoms of that element. We'll talk more about the atomic number a little bit later in this video, but as we'll find out, the atomic number defines the number of protons. And this is another case where Dalton's atomic theory had to be revised. In Dalton's time, protons had not been discovered yet, and so there was no notion of atomic numbers. And so what Dalton thought was that masses defined an element, and we now know that's not true. What defines an element is its atomic number. Dalton proposed, and we still understand this to be true, atoms of one element differ from others in their properties, and all elements have different properties. And so what gives us compounds is that a compound consists of 2 or more elements combined in small whole number ratios. And so in a given compound, the number of atoms of each element is always the same. And then the last piece, atoms are neither created nor destroyed during chemical reactions. Right? All that happens during chemical reactions is that the atoms change how they're connected to one another. But we don't create or destroy. We don't get any new atoms. We don't lose any atoms over the course of a chemical reaction. All right, and so let's just take a look and see how this atomic theory can explain the laws that we initially talked about. Right, so the law of conservation of mass tells us that in a chemical reaction, matter is neither created nor destroyed. Well, that's covered by the 5th postulate in Dalton's atomic theory. Dalton says that atoms can't be created or destroyed. All that's happening in a chemical reaction is we're changing how they're connected to one another. So if we could observe atoms, right, what we would see over the course of a chemical reaction is that in the reagents, we have these yellow and magenta atoms connected in one arrangement, and then in the products, they're connected in a different arrangement. But the number and types of atoms don't change. I had 2 yellow atoms, I have 2 yellow atoms. I have 6 red atoms, I have 6 red atoms. So the numbers of atoms of each element is conserved in a chemical reaction. And so that's why the mass doesn't change, because I have all the same material present, I've just changed how everything is connected together. And then the law of definite proportions and law of multiple proportions, that's largely covered by the 4th postulate in Dalton's atomic theory. Right, he said that a compound is defined by the number of atoms that make it up. And we now know it also depends on exactly how they're connected. But water has the chemical formula H2O, meaning there are 2 hydrogen atoms and 1 oxygen atom. It doesn't matter if we find water from New York State, or California, or China, or Mars, or Jupiter, or in some other solar system, it will always consist of 1 oxygen atom and 2 hydrogen atoms. And so that's why the ratios of the elements are always the same. And then in terms of the law of multiple proportions, I can certainly make different compounds using the same elements. In this case, water has the formula H2O. A different compound that you may have under your sink, it's often used as an antiseptic, is hydrogen peroxide. In hydrogen peroxide, we always have 2 hydrogen atoms and 2 oxygen atoms, right? But in a different compound, I can't have a third of a hydrogen atom, or I can't have a third of an oxygen atom. I always have to have whole numbers of atoms, and so that's why in the law of multiple proportions, we always saw that the ratios of the elements that combined with one another were always whole number ratios of one another, because I can add a whole nother oxygen atom to all of the hydrogen peroxide molecules. I can't add a fraction of an oxygen atom to it.